Welcome to our video abstract on performance assessment of GNSS diffraction models in urban areas. My name is Guohao Zhang. The GNSS is subject to various interference in urban areas, including the building obstruction, multipath effects, NLOS reception, and diffraction. Among those effects, the diffraction has always been overlooked. From a real experiment, the diffraction effect is actually quite common in urban areas, which attenuates the carrier-to-noise ratio and degrades the related algorithms. To mitigate such degradation, we may need to model the diffraction. To do so, there exist two popular methods. One is the knife-edge model. The GNSS signal propagates as a wave. The wavefront of a satellite emits secondary wavelets, and those wavelets will continue to form another wavefront for propagation. The knife-edge model simplifies building as a knife edge and describes diffraction by the spatial integral of those unobstructed secondary wavelets. However, the 3D spatial integral becomes complicated for the urban environment. Another approach is the UTD model, which describes diffraction as a local effect dominated by a specific ray. It can strictly estimate diffraction based on the geometrical parameters, but with additional computation loads. In this study, we'll provide detailed procedures of GNSS diffraction simulation on carrier-to-noise ratio and pseudorange. Then we'll assess the diffraction modeling performance for the low-cost receiver in the urban area. To assess the performance, we'll firstly apply ray tracing algorithm based on the satellite position, receiver location, 3D beam model to obtain the geometrical parameters for simulation. Then we'll apply knife-edge model and the UTD to obtain the diffraction coefficient. By combining with the open sky carrier-to-noise ratio model, we can simulate the diffracted carrier-to-noise ratio of a measurement. During the UTD method, we can also simulate the diffracted pseudorange measurement based on the geometrical parameters and other error models. By comparing with the simulation result with the measurements from real experiments, we can evaluate the performance of each models. We firstly evaluate the performance in a scenario with only one building. Here, the diffraction occurs even when the satellite is blocked by the building with more than 10 degrees of elevation angles. From the result, we can see both methods can achieve satisfactory performance on diffraction simulation. For a more complicated scenario with multiple buildings, the UTD outperforms the knife-edge model on diffraction simulation, including the transition from diffraction to line-of-sight and back to diffraction. From our results, the diffraction can frequently occur in urban areas, and we also prove they are legitimate. The UTD can achieve more accurate diffraction simulation, but with higher computation loads. The diffraction simulation is sensitive to the accuracy of building models nearby the receiver. Our study can contribute to the realistic GNSS simulation in urban areas, which is helpful to many other studies such as the collaborative positioning. Then, the diffraction simulation can provide us more information about the GNSS measurements, which is able to help us to develop an advanced 3D mapping-aided GNSS positioning algorithm. If you are interested, you can find more details in our paper or contact us. Thank you for watching.